Okay, guys, so today we are going to be talking about periodic trends. If I could just get this to pop down real quick. Okay, so the first periodic trend that we're going to talk about is electronegativity. Okay, so electronegativity will increase going up and to the right of the periodic table. Up and to the right. Electronegativity is the ability of an atom to attract shared electrons in a covalent bond. The higher the electronegativity value, the more strongly the element attracts the shared electrons. Okay, so for instance, if we're seeing Na and potassium, which one has a higher electronegativity? Na is above potassium, so Na would have a higher electronegativity. It'll attract shared electrons. Then let's compare carbon or fluorine. Fluorine will have a higher electronegativity than carbon because it is further on the right of the periodic table. So it's going to increase going up and to the right. These are some values that you have to memorize. And there's some tools to be able to memorize those. So if you do the second row, you start at 1, add 0.5 each time to get all the way to 4. Then memorizing 0.9, 1.2, finding little tricks to help you memorize. So you need to memorize all these electronegativity values. So rank oxygen, sulfur, cesium, and barium in the order of decreasing electronegativity. Decreasing electronegativity. Okay, so remember, it increases going up and to the right. Oxygen, sulfur, cesium, and barium. Okay, so let's do those in a color I haven't circled on the periodic table. Let's do purple. So we have oxygen, sulfur, barium, and cesium. Okay. So if electronegativity increases going this way, electronegativity increases, I want to do the opposite. I want to go from biggest to smallest. Biggest to smallest when I talk about decreasing. So highest electronegativity to lowest. So the highest one will be oxygen. Then I will have sulfur. Then I will have barium. Then I will have cesium. Okay. Another question is, what's the electronegativity difference between hydrogen and fluorine? Hydrogen is 2.1. And fluorine is 4.0. So 4.0 minus 2.1. That equals 1.9. These are some types of questions that you may see on your tests. Atomic radius is another periodic trend that we're going to talk about this unit. atomic radius increases going from going on the bottom and to the left. It increases this way. So the atomic radius is how far from the center of the nucleus to the electrons. How far is it to the center of the nucleus? All the way to the electrons. So the highest ones would be on the bottom of the periodic table and all the way to the left. As you can see over here, fluorine is quite tiny, and so on. So rank them in order of decreasing radius. So the same ones that we did last question. So remember, decreasing is biggest to smallest. And remember, it increases as we go down and to the left. Okay. So we're going to increase going this way. Atomic radius. Okay, so I want the biggest atomic radius because I want to put it in decreasing order. So I'm going to put cesium first. That's the biggest because it's the furthest to the left and on the bottom. Then I'm going to put barium. Then I'm going to put sulfur. Then I'm going to put oxygen. Okay? Moving on. Now we're going to talk about ionization energy. It has the same trend as electronegativity. It's going to increase going up. Let's pick a different color. Going to increase going up and to the right. This is the amount of energy required to move an electron from the gaseous form of that atom or ion. Remember, electronegativity was to attract an electron. Ionization energy is to remove an electron. So which of the following atoms has the highest first ionization energy? So we have sodium, potassium, scandium, and rubidium. Sodium, potassium, where are those? One sec, guys. I don't know why, but I feel very, very blind right now. Oh. Okay. So, we are going to increase going up into the right. Okay? So the one furthest to the right is going to be scandium. Which one has the lowest first ionization energy? So when we say first ionization energy, this means to take away one electron. So it's gonna use a lot of energy to take away that one electron from scandium because it has the highest ionization energy. Now we're gonna look at which one has the lowest. Obviously the one on the bottom and to the left. That would be rubidium. Now we're doing electron affinity. So electron affinity is going to be the degree to which an atom or molecule attracts additional electrons. Remember, electronegativity was to attract them in a covalent bond. This is just single electrons. And again, it's going to have the same trend as ionization energy and electronegativity. It's going to increase going up and to the right. Metallic character is going to be like atomic radius. It's going to increase as we go to the left, because we know that the metals are over there, so obviously metallic character will increase, and it's going to increase as we go down as well. So the periodic tens all laid out for you. Metallic character and atomic radius are both going to go increase as you go down and to the left. Everything else will increase as you go up and to the right. So now we're going to do some quantum review. So we did this topic last unit and we didn't have a great grasp on it, so let's go ahead and review it again. In quantum mechanics, this is our way, the quantum numbers are our way of showing where electrons are and their wave behavior. So you can't know the exact location, but we can figure out the most probable location, like what orbits they are and what block and things like that, what ring, what shell number. Not all locations are possible, and that's why we get the quantum number boundaries. But there are rules for where electrons can be found. Okay, so N is going to be your distance away from the nucleus, your energy level, also known as your shell number. So N is typically your period number. So if you could be 1, 2, 3, 4, 5, and so on. L is the shape of the orbit, also known as a subshell. So for L, you are going to have 0, 1, 2, or 3. S, if you're in the S block, you're going to have a 0 for your L value. If you're in the P block, you're going to have a 1. If you're in the D, you're going to have a 2. If you're in F, you're going to have a 3. ML is the orientation of the orbit, and you find ML using negative L to positive L. Okay? So if you have a S value of 0, ML, too thick, ML is going to be just 0. If you have a P value, if you're in the P block, you have an L value of 1. So ML will be negative 1, 0, 1. If you are in the D block, your ML will be negative 2, 1, negative 1, 0, 1, 2. If you're in the F block, ML will be negative 3, negative 1, negative 2, negative 1, 0, 1, 2, 3. Okay? This is where our boundaries come into play. You can only have certain numbers for ML. And then for spin, it's either positive or negative 1/2. Positive is up, negative is down. As we see in our electron configuration orbital notations, one goes up and one goes down in each orbital. Okay? And then also with the ML values, you can determine the number of orbitals. So we only have one number, so there's one orbital in the S block. That's why when we write 1s, we go one up and one down. The dash is one orbital. There's 3 numbers in the ml value, 3 possible ml values. So that means you have 3 orbitals. So that's why we have to P6, we have 1, 2, 3 orbitals. Those are orbitals. And then now we have in the D block 1, 2, 3, 4, 5 orbitals. So that's why in 3D, for example, you'll have 5 dash lines. So quantum numbers give us all of these extra things that you're trying to memorize, but just learn the quantum numbers and the rest will come to you naturally. You'll learn it, not memorize. Okay. So we have our subshells S, P, D, and F. And these are the shapes that go to them and their L values. Again, L for S is 0. For P, L is 1. For D, L is 2. And for F, L is 3. And as I just explained right now, how to get ML values, you go from negative L to positive L. It's going to describe the orientation of the orbit. Okay, so that shape that we just talked about, that shape can be lined up in different ways. So that's ML is going to tell you how many ways it can be lined up. So if you're the P atomic orbital, then you can be lined up in 3 ways. If you're the S, you can be lined up in 1 way. If you're D, you can be lined up 5 different ways. If you're F, you can be lined up 7 different ways. So magnetic quantum number, ML, tells you how many orientations. Magnetic spin, again, positive, your electron is going to go up. And then negative, your electron is going to go down. You can only have positive or negative 1/2. So quantum boundaries. So for instance, in the first, in n equals 1, we talked about this in the first row, there is only the S block. So in the first row, you only have L equals 0. So if you ever see n equals 1, L must equal 0, then ML must also equal 0. This thing is supposed to have M right there. And you can only have positive 1/2 or negative 1/2. So in 1s2, you can only have one going up and one going down. That's what that means. Okay, n equals 2. You can either have 2s or you can have 2p. Okay? And again, for 2s, you can only have ML be 0. Because negative L, 0 to positive L, 0 is 0. When 2p, L equals 1, so you go negative 1 to positive 1, and these are the possible ML values that you get. Okay, and then it goes on and on. N equals 3, now you have S, you have P, and you can also have D. And again, they're L, 0, 1. And then this one's supposed to be 2. So the negative D will be, ML will be negative 2 to positive 2. In P, it'll be negative 1 to positive 1. And 0 ML is obviously 0. Okay? Just make sure you keep on going over periodic nomenclature. So you should know your groups, your families, your blocks. So groups are and families are both the columns. Blocks S, P, D, and F, which we're focusing on in this unit. Main group are S and P blocks. Transition metals, this is your D block. Lanthanum and actinium series, these are going to be your F block on the bottom. Alkali metals, first group. Alkali earth metals, second group. Halogens are going to be fluorines group. Noble gases are going to be the last group. Know what shell is. So shell is the N equals 1, N equals 2, N equals 3. Subshell, again, S, P, D, F. And you should know orbitals are 2p, 3p, 1s, nonmetals, metals, and metalloids. Okay, moving on. Okay, so when doing electron configurations, know your 3 rules. Aufbau says that you must go in order 1s2, 2s2, 2p6, 3s2, and so on. You cannot skip until you fill each one of them. Aufbau says to go in order. Line up. Hun says to spread out your electrons. So as we were talking today, you have to put 1 in each orbital, like you do up here. You can't pair, cannot talk. Cannot pair up until, I cannot spell either, until each orbit has 1 electron. Then Pauli says only 2 people per room. Only 2 people per room. Only 2 electrons in an orbital. So for instance, a common one that you'll see on questions is them having 1 down, 1 up, and then 1 up again. That's 3 per room. He also says 1 must go up and 1 down. So only 2 per orbital, and they must be in opposite directions. And we are done.